Hamera and Venkat Dashira, they agreed to give a talk, and he will be talking about phase transition in of iron in iron phosphate and oxidative dihydrogenating reaction, dihydrogenation reaction. So, all yours.
Thank you, Chairman. Today I want to talk about some of my research experience, that what I observed by usage of the mass flow spectroscopy in my project. And the title of my presentation will be the phase transformation of the iron in iron phosphate in the oxidative dehydrogenation reactions. Just to give a little bit introduction, like what is my project about, is to prepare the alkyl methacrylates, which are the important precursors in the manufacturing for the polymers and dyes and adhesives. And the oxidative dehydrogenation of the isobutyric acid over the iron phosphate catalyst, which are prepared by the ammonia gel method, which is supported on silica, is a more viable route for this production of ethyl methacrylates. And this catalyst was tested under a gas phase catalytic reactor in a continuous fixed bed microflow reactor in a downflow mode. And in these reactions, A was used as an oxidant and nitrogen was used as a diluent. To get more insight, let me show the schematic diagram of the reactor that what I used, which shows two cylinders of nitrogen and A, which comes with an high pressure gases, which goes towards the reactor, and then feed is actually pumped through the high pressure pumps. And that catalyst was placed as the iron phosphate is in the heating block, which will be in the temperature range of 300 to 500 degrees centigrade. And all these products are actually qualified by using the GC and GCMS analysis. But one of the major drawbacks of these gas phase oxidation reactions is, instead of actually the reaction going towards our target product, there are several reaction pathways going in the same time. And as in the red block, that's showing the production of the ODH of EIB to EMA, but at the same time, the formation of other unwanted products like carbon oxides, acetaldehyde, and other cracking products like ethane, methane, propane were taking place. The main influence of these side reactions is the phase transformation of our catalyst that's happening inside our reactor. So if we have to control all these reactions and to go towards our target product, we need to control the phase transformation of the iron that is happening on the iron phosphate catalyst. But another drawback that what we observed when we're proceeding in our project is that lifetime of this catalyst. In an industry, the lifetime of a material is very important because it defines the whole economics of the industry and the profits and the losses. But here if we see that whatever the material that we used, that it is only stable until 20 hours. And actually after the regeneration step is to carried out with the using of the air initially, and even with the first regeneration and the second regeneration, if we observe, that it actually showed the low yield towards our target products like ethyl methacrylates. So at every regeneration step, the yield towards our ethyl methacrylate is being decreased. That's a very disappointment after our going through the middle of our project. So that to investigate what's happening, what is the reason to decrease the yield of these products, we use different characterization techniques. That's one of the most important thing is the in situ XRD under hydrogen. That one in situ XRD under hydrogen showed the phase transformation of an iron phosphate to the iron pyrophosphate, and in situ XRD under air showed the transformation back to the iron phosphate, and it didn't show any other extra phases that is present and happening in the catalyst. And whatever the results that what we obtain from the in situ hydrogen or in situ oxidation is reliable with the mass van Kelvin mechanism. That's the primary mechanism in the oxidative dehydrogenation reactions to form the ethyl methacrylate from the ethyl isobutyrate. And we took the help of the different characterization techniques like chemisorption and hydrogen oxygen titration and electron vapor deposition method to prepare the catalyst in different ways, but we didn't overcome this problem. Then we came through the mass flow spectroscopy to see what are the phase changes that's actually happening in this iron phosphate catalyst. For those experiments, we took 4 batches of the catalyst. One is the fresh iron phosphate that is actually calcined and unused, and the second batch is the after reduced with the hydrogen, and the third one is the oxidizing at a lower temperature, that is oxidizing the reduced catalyst below 500 degrees, and oxidizing the reducer catalyst above 550 degrees. As you show in the Moskva spectra, like the four different type of catalysts show the totally different patterns, which given more insight like what's happening in the phase transformation of these catalysts. And the Moskva parameter showed that the calcined iron phosphate contains like an 100% iron phosphate triromite phase, but after it is reduced to the major portion of the iron pyrophosphate, and the minus still is like the iron phosphate is still in the triromite phase, which is actually in contradiction to what we observed in the in situ hydrogen before, that as the total iron phosphate is totally transformed into the iron pyrophosphate, and there is no traces of the triromite phase is observed. But in the Moskva spectroscopy, we observed like a site fraction of like 27% towards the triromite phase. That's actually like an acts as an impurity. And then after the low temperature oxidation, that is below 500 degrees when we oxidized it, we formed like an alpha iron phosphate, and still there is a 32% of iron pyrophosphate is left. That means actually the reduction is not actually happening in like in one single step as we observed in the in situ hydrogen or in the reaction in a fraction of seconds. It is happening in two different steps. And the high temperature oxidation showed like in 79% of the phos phase, and the rest is the alpha phase. So that the oxidation is also happening in the two different steps, and the reduction is also happening in the two different steps. So what we can conclude is that spectral parameter of the calcined catalyst occurred the 100% iron plus 3 species, and after the reduction it is reduced to the Fe2 plus species, that is the iron pyrophosphate. And after the reoxidation, only like a 50% is actually in the Fe3 plus component, and still there is an Fe2 plus component is present in the low temperature oxidation. But the high temperature oxidation, like above 600 degrees, like 79%, like the major fraction is the Fe3 plus phases. So after all these conclusions, like we draw a schematic diagram of like what is the reduction and reoxidation of the iron phosphate happening. That's in between 550 to the 660. Iron phosphate is actually transforming to an Fe3P2O7, which is an intermediate phase, and at higher temperatures, it is actually going to the pyrophosphate phase. And at the initial oxidation, it is going to the alpha phase, and after it is totally transformed to the quas type phase. Unfortunately, we couldn't detect all these phases in the in situ XRD means, because due to the excessive overlap of the iron pyrophosphate and the alpha phase and the quas phase of the peaks, and which is even very difficult to do the Rietveld refinement analysis on these phases. So, after we got the investigation of what's happening under the reduction and oxidative environments, then it given more insight to us to investigate what's happening under the really oxidative dehydrogenation environments. So as we observe from the hydrogen and the oxidation, like it is happening in the two steps, and the temperature of the reoxidation is also affecting the formation of these phases. So we defined like 4 conditions to investigate the phase transformation of this iron phosphate. That is, with the isobutyric acid alone, and by passing the isobutyric acid and water throughout this catalyst, and passing the isobutyric acid and the ethanol, which is called as an organic co-feed, and isobutyric acid plus water plus ethanol, which is called as a combined co-feed. And all these transformations is done under the reaction conditions. Those are the 300 to 500 degrees centigrade. And the contact time with the feed to the catalyst is very minor, that's 0.8 seconds. And fuel to oxidant ratio of like 1:0.73. That means we are actually doing our reactions in very reduction environments. And the water ratio is like 1:50, and ethanol is 1:1. All these conditions are actually established by calculating the selectivity towards our target product, and these are the optimized conditions. So we decided to run these phase transformation reactions under these conditions. Unfortunately, we don't have the in situ Moskva facility to be equipped with this reactor. So all the catalysts were analyzed after the 500 degrees, which are cooled under the positive flow of nitrogen. And with the isobutyric acid, which is showed like same as the fresh catalyst, that is the Fe3 plus phase present, that's the triromite phase. But the difference is observed when we use it like an organic co-feed, that is the methanol, and a water co-feed, and a combined co-feed of like a water and methanol, which showed like a total different phases present in the spent catalyst. Thus with the organic co-feed, that the iron pyrophosphate is present, and then alpha phase and then beta phase is also present. That is actually, we related that one with the deactivation of the catalyst after like 7 hours. Because if this transformation is taking place, then the formation of the beta phases will be increased, which is an inactive phase, which decreases the yield towards our target product. And with the water co-feed, we observe the minor quantity of the iron pyrophosphate and the major of the alpha phase. And this is also observed in the selectivity towards our target product, thus the alpha phase of the iron phosphate is very active, and which is actually supported in the literature. And then the combined co-feed, which showed like an 60% of an iron phosphate and the 32% of an alpha phase, which is existed in 3 other phases, but the oxidation state of iron is still in +3 phase. And which is observed in the increase in the EID conversion, which increases the yield of the EMA that towards all the other ones when we're using the water and the ethanol co-feed and with the ethanol too. Like the conversion of EID is very increased, that is due to the presence of the alpha phase present in the catalyst, that is dominated by the Fe3+ phase and then synergetic effect between the alpha phase and the iron pyrophosphate phase. And the Mossbauer data of the combined co-feed spent catalyst showed there is an Fe2+ spectral component and Fe2P2O7 is also there. But as I told you, the lifetime of these catalysts are very small, so that only these catalysts are active until like 72 hours. So that to increase this lifetime of these materials, we use it like different promoters like potassium, rubidium, and cesium. And among them, like I'm presenting only the results of the cesium catalyst because the other promoters that we are still doing the investigation. So like for the cesium to iron ratios, we tested on the 3 different ratios of like 0.10, 0.15 and 0.25. But total 3 ratios are also showed the same type of effect. So that to give the information, I'm only showing the cesium to iron ratio of like 0.10. And the fresh catalyst and after the reduction and after reoxidation showed like a formation of the iron pyrophosphate and then alpha phase. Here we didn't took the low temperature reduction, low temperature oxidation and then high temperature oxidation because the formation of the cesium promoted the formation of an alpha phase at a lower temperature. But the presence of the cesium didn't influence the reduction and reoxidation pathway of the catalyst. And the same type of conditions actually we observed for the cesium promoted iron phosphate catalyst, but unfortunately we didn't even observe any difference in the formation of an iron pyrophosphate phase or an alpha phase with the promotion of the cesium. So that my future work concludes like the promotion with the other materials like sodium, silver, and to see the stabilization of these phases under the reaction conditions. So to conclusion, that the Mossbauer spectroscopy has provided very useful providing an understanding the phase transformation of the iron phosphate catalyst. So that actually we can stabilize the alpha phase under the reaction conditions towards our target lifetime and the target yield towards our products. And the characterization of the spent catalyst given the new insights like what's happening under the reaction conditions. And addition of the water during this phase, during these transformations, given the new phase called like an alpha phase, that is actually a catalytically active phase, and removing this water is going back to the formation of an beta phase. Unfortunately, there is no effect of cesium on this reduction or reoxidation pathways, but in future we will investigate with the silver and sodium. And I would like to acknowledge University of KwaZulu-Natal, SASO, and Ithamba Labs for the infrastructure, and the conference organizers to giving me this opportunity. And at the end, thank you for having a great audience like you. Thank you.
Thanks very much. It's open for discussion.
Thank you guys.
Yeah.